Up till now, I have been discussing about crystals, what crystals are, how atoms are arranged in a regular and periodic fashion in 3 dimensions in crystals, what is meant by the crystal systems, unit cells, lattice parameters, etc. Then I discussed about the way atoms are arranged at the lattice positions and also how atomic groups are arranged throughout the 3 dimensional crystals. Now, the thing is, with the naked eye, it is not possible to figure out the locations of atoms in the unit cells of crystals, but it is very important to know the structure of actual crystals, what kind of crystal system they have, what kind of lattice parameters they have, what is the unit cell like, etc., etc. So, how we are going to do that? Why this is so important to know about the structure of crystals? Because the structure of crystals will dictate what kind of property the material is going to have. And since we cannot see through the crystal with our naked eye, we need to send some kind of an agent through the crystal, so that that agent will bring in all the information from within the crystal. So, this we normally do by using what are known as X-rays. So, in this lecture I will deal with the basics of X-rays. Now, X-rays were discovered by the German physicist Röntgen. It was discovered in 1895 by the German physicist Röntgen. He found this new kind of rays from his experiments, which have lot of similarities with ordinary light, in the sense that these X-rays, they are electromagnetic radiations as is ordinary light. Now, X-rays can affect photographic films in the same manner as ordinary light. X-rays can travel in straight lines like ordinary light, but there are some basic differences also. X-rays are much more penetrating than ordinary light, and the X-rays waves are much shorter than light rays. Now, here is the electromagnetic spectrum, which shows the different types of radiation with their frequencies, and this is the range for visible light, and this is where the X-rays come. Normally, the wavelength of X-rays we use in the study of crystals is about 0.5 to 2.5 angstrom wavelength. So, this is normally the wavelength of X-rays which we use to study crystals. On the other hand, the average wavelength of visible light is of the order of, say, about 6,000 angstrom. So, you can see that X-rays are much more penetrating than ordinary light. So, this has got certain advantages which we normally utilize to study crystals with. Now, as we have already mentioned, that X-rays are electromagnetic waves. So, what is an electromagnetic wave? That means X-rays are associated with both an electrical field and a magnetic field. So, if this is the direction of propagation of X-rays, say in the x direction, then in the y direction you can find an electric field associated with the wave, and in the z direction you can find a magnetic field associated with it. Since the magnetic field is of no concern to us in this study, we are not going to mention it at all. So, it is the electric field that we will talk about. Now, the electric field and the magnetic field, which they can assume any direction in the yz plane. So, if you consider the yz plane, in the yz plane the electric field and the magnetic field, which are perpendicular to each other, they can assume any position in the xy plane. If that is the case, we say that the radiation is unpolarized. On the other hand, if we could have the electric field lying in the xy plane, in that case we will say that the wave is polarized. Now, the electric field is a function of both time and space, and this is how the electric field varies with respect to distance and with respect to time both. Now, how X-rays are produced? Now, X-rays are normally produced by allowing a beam of highly energetic electrons to strike a metal target. Now, this is a typical schematic cross section of an X-ray tube, and here we have a filament or a cathode made up of, say, tungsten, and when a current is passed through this filament, there will be thermionic emission of electrons. And if we have an anode or a target made up of metallic material or an alloy, and if a high potential is maintained between the anode and the cathode, and the high potential may be of the order of, say, 30,000 volts or even more, then what will happen? The negatively charged electrons will be drawn towards this anode or the target, and due to the impact of these electrons, some X radiation is produced, which is invisible to the naked eye. And in the tube, which is a highly evacuated one, you provide some windows made up of very thin low absorbing material like beryllium, and you can take the X-rays out of the tube and you can utilize that X-rays for all crystallographic purpose. Now, due to the impact of the electrons with the target becomes heated to a great extent, and that is why the target must be kept cool by passing cooling water, otherwise the temperature of the target will become very high and the material may melt. So, the kinetic energy of an electron of charge E passing through a potential difference of V will be equal to EV, and that can be equal to half mv square, where E is a charge on the electron, V is the voltage across the electrodes, m is the mass of the electron, and small v is the velocity of the electrons. Now, let us suppose that we have a target made up of molybdenum. Say we have in the X-ray tube a target made up of molybdenum, and we start with a potential difference of 5 kV between the anode and the cathode. So, what we observe? We observe from the tube the X-ray that comes out is made up of a large number of wavelengths. So, those wavelengths are so close that we can plot the intensity of individual waves and their wavelength by a smooth line of this type. Say we have maintained a potential difference between the anode and the cathode, which is of the order of 5 kV. So, we produce quite a few the radiation that is coming out of the tube is made up of a number of wavelengths, and the wavelengths are very close to one another. So much so that the wavelengths that are produced, if we plot their intensity and the wavelength, we can draw it by a smooth line of this kind. Well, we should know very well a smooth line, the meaning is the wavelengths that are produced are discrete, but since they are very close together, we can denote them by a smooth line of this type. Now, let us say increase the potential to 10 kilovolt, and then again say if we measure the wavelengths of X-rays coming out of the tube and the intensity of each and every wavelength, and if we plot the intensity versus wavelength, we get a curve of this type. Then if we go for say 15 kilovolt potential difference, then it goes in this fashion. With 20 kilovolt, it goes in this fashion, and for the molybdenum target, when we apply a potential difference of 25 kilovolt, then over and above a host of wavelengths that we get two very sharp wavelengths as shown by these two lines over here, and these wavelengths over here, these wavelengths, this and this, are known as the characteristic radiation. So, to begin with, before we go up to 25 kilovolt, whatever voltage we apply across the anode and the cathode, we get a host of radiation, different wavelengths. So, that host of radiations of different wavelengths is known as the white radiation or heterochromatic radiation, white or heterochromatic radiation, many wavelengths. But what happens when we raise the potential to 25 kV, over and above the white radiation, we get two very sharp wavelengths, very high intensity compared to the rest, and these are known as the characteristic radiations. So, these are known as the characteristic radiation. So, why it is called characteristic? Why and what it is characteristic of? It is characteristic of the target that has been used. So, if you use a molybdenum target, the characteristic radiation starts coming at say 25 kV and more. For some other target, the characteristic radiation will appear at a different voltage. So, that is why the characteristic radiation is very much dependent on the target material. It is a characteristic of the target material. Now, this wavelength here is known as the K beta wavelength. This wavelength is the K beta, the shorter one, and the more intense characteristic radiation of a larger wavelength is known as the K alpha radiation. When we study the intensity versus wavelength plots at different potentials across the anode and the cathode, we realize two things. One is, at any particular voltage used, there is a minimum wavelength radiation that is obtained. For example, when the potential is 5 kilovolt, we find that this is the minimum value of the wavelength that we get in the white radiation. Now, when we increase the potential to 10 kV, then what we find? We find that this limit of wavelength which we got in case of 5 kV, now it becomes even shorter. So, for 10 kV this minimum wavelength that we can get is shorter in case of what we got at 5 kV. So, this limit is known as the short wavelength limit or SWL. So, this limit is known as a short wavelength limit or SWL. Now, as we increase the potential even further to say 15 kV, again we find that the short wavelength limit goes to even shorter value. So, two things we notice. One, the maxima in the plot, it shifts towards the, it improves the maxima, the value of the maxima goes up as we increase the potential. Not only that, it shifts towards the left, and at the same time the short wavelength limit also goes to shorter values. So, this is after 15 kV potential between the anode and the cathode, and when we apply a potential of 20 kV, this is the kind of plot we get. The short wavelength limit is then even shorter, and at 25 kV we find it is even shorter. Now, if we increase the voltage to more than 25 kV in case of molybdenum target, the entire plot shifts in a manner similar to the other ones, and these characteristic radiations also become more sharp. So, as I mentioned, this characteristic radiation is called the K beta radiation, and this characteristic radiation is known as the K alpha radiation. K beta radiation wavelength is shorter than that of K alpha. Now, if we use, as I already said, another kind of material as a target material, say nickel or iron, we will find beyond a certain voltage corresponding to that metal, you will again get the characteristic radiation over and above the white radiation, but the threshold voltage will be different. So, it depends on the target material at which threshold voltage the characteristic radiations will appear. Now, if we look at a single electron when it of charge E, after going through a potential field of magnitude V, now we can write E V is equal to h nu max. After all, nu max is the maximum wavelength for the electrons. So, nu max we can write is equal to C by lambda SWL. You see what happens when the beam of electrons from the filament strikes the target. You see, after striking the target, it may so happen that one of the electrons, it will lose the entire amount of energy it has in one impact, and the X-ray photon coming out of that impact will have the highest amount of energy and smallest wavelength. Maybe another electron which strikes the target loses only a part of its energy. So, the corresponding X-ray photon that is produced will have low energy and it will be having a higher wavelength. So, since we are dealing with a large number of electrons coming from the cathode and striking the target, so what will happen? We will have a number of cases. In one case, some of the electrons will lose all their energy in one impact, and their total energy is converted into the energy of an X-ray photon. So, those X-ray photons will be the ones having the highest amount of energy associated with them, and therefore, the lowest wavelength value associated with them. The other electrons, may not be losing the entire energy in one impact, and there can be so many variations. So, due to the impact of thousands and thousands of electrons, we will get a host of X-ray photons of varying energy, which are quite different one from the other. So, we will get a host of electrons, host of X-ray photons coming out due to the impact of the electrons with the target material, and these host of X-ray photons that are coming out, they will have all kinds of energy, and therefore all kinds of wavelengths. And that explains why when we have an X-ray tube, from the X-ray tube we get a large number of X-ray wavelengths, or we get the white radiation. So, when we look at the lambda short wavelength limit, which is associated with the electron having the highest energy, we can simply write as lambda SWL is the lambda minimum. It will be C by nu max from these two equations is equal to hc by EV. And so, if we put the value of Planck's constant, value of the velocity of the electrons, charge of the electron, and the voltage we use, we can find out lambda SWL in angstrom will be equal to 12.4 into 10 to the power 3 divided by V, where V is the voltage, applied voltage in volts. So, you see that for any particular applied voltage, you can find out what should be the lambda SWL, or the short wavelength limit. Now, if we look at the white radiation, which is also called the continuous spectrum, the intensity of the white radiation of the continuous spectrum is equal to A I Z V to the power m, where A is a proportionality constant, I is a tube current, Z is the atomic number of the target, V the voltage, m is a constant with a value of about 2. You see, sometimes it is necessary, as we will see later on, to have a white radiation of sufficiently high intensity, for some particular crystallographic work. So, how to get a high enough intensity of the white radiation or the continuous spectrum? Now, as you can see here, there are several possibilities. One of the possibilities is, the value of Z. Say, if you increase a target of a sufficiently high atomic number, that will immediately give you a high value of I of the white radiation. For example, in many cases we use a heavy metal target, say for example tungsten or molybdenum, in order to get a high enough intensity of the white radiation. Now, if we look at the characteristic radiations that are obtained due to the impact of the electrons with the target, we produce, as I already mentioned, two characteristic radiations like K beta and K alpha. Now, this table gives us an idea of the wavelength of the K alpha and K beta radiations for different target material. For example, if you have a molybdenum target with an atomic number 42, this is the wavelength of the K alpha radiation in angstrom, and this is the K beta in angstrom. So, for copper 1.54178 angstrom is the wavelength of K alpha, and 1.39217 the wavelength of the K beta radiation. So, in this way, you can have different values of the wavelengths of K alpha and K beta from the different targets, and as we will go through this course, we will find that how we are going to use them for crystallographic purpose. Now, if we look at the K K alpha radiation, it appears to be single wavelength, but in fact it is made up of two wavelengths very, very close by. So, it is a doublet of K alpha 1 and K alpha 2. Now, when we look at the intensity of the characteristic lines, intensity of the characteristic line can be given by an expression of this type B I V minus V k to the power n. Here B is a proportionality constant, V is the applied potential, then V k is what is known as the K excitation voltage, or is the threshold voltage beyond which the characteristic radiations will appear. So, it is that voltage below which there will not be any characteristic radiation produced and above which the characteristic radiation will be produced. So, V k is a K excitation voltage for that particular target. It is not the same for all targets. So, V k will differ from target to target. I is the tube current, the current passing through the filament, and small n is a constant with a value of about 1.5. Now, it was Moseley who found out a relationship. It was Moseley who found out a relationship between the wavelength of X-rays and root over nu, the frequency of the waves, for different characteristic radiations. Say for example, the K alpha 1 radiation. So, if you plot atomic number versus root nu, they found out that there is a straight line relationship. Now, on this axis the lambda is given, the wavelength of the X-ray. So, you see that there is a straight line relationship existing between the atomic number and root nu, and this relationship was found by Moseley and is known as Moseley's law. Now, before we come to discuss the interaction of X-rays with matter, I would like to tell you about how white and characteristic radiations are produced from an X-ray tube. So, as you have seen, when a high energy electron beam falls on the target, X-rays are produced. Now, what is the mechanism? Say here we have got one atom of the target material. So, this atom will have a heavy nucleus, the center, and the electrons will be arranged in K shell, L shell, M shell, etc., etc. So, when high energy electrons are incident on this atom in the target material, if suppose there is an electron here in the K shell, or an electron in the L shell, or an electron in the M shell, the moment high energy electrons are impacted, when they strike against these electrons, then these electrons momentarily will take away quite a bit of energy from the striking electrons. So, momentarily they will be accelerated, and according to theories of electrodynamics, any accelerated charge will give out energy. So, what happens when these things happen, when there is an impact, then this electron here in the K shell of the target material, it will start to give away the extra energy it got due to the impact in the form of radiation in all directions. Similar thing will happen, to the other electrons also. They will give up the extra radiation, extra energy it got from the striking electrons, and it will give it out in the form of X-rays in all possible directions. So, these electrons in the atom of the target material, actually what they do, they scatter, so to say, the incident energy obtained from the striking electrons. So, the process is called the scattering process. The process is called the scattering process. So, when a beam of electrons strikes the atom of a target material, the electrons in the atoms of the target material which are impacted start acting as scattering centers, and they scatter that radiation, that X-ray, in all possible directions. So, this is the origin of the white radiation, and the amount of energy which a particular electron in the atom of the target can have from the striking electrons will vary a lot, and as a result the wavelength that will be produced will also vary a lot, and the totality of all the wavelengths coming of X-ray wavelengths coming out of the target material, it will constitute what is known as the white radiation or the continuous spectrum. Now, suppose if a situation arises such that the electrons are having energy sufficient to knock out an electron from the K shell. Say for example, the striking high energy electrons are so strong energetically that they can knock out an electron from the K shell of an atom. So, this is a K shell atom, say this is knocked out of the atom by the striking electrons. Then what will happen? In order to minimize the energy of the system as a whole, there will be electrons coming from say the L shell or the M shell to occupy the vacancy over here. So, when this electron is struck out, knocked out from the shell, K shell, it comes out. So, this vacancy will be filled up by either an electron from the L shell or the M shell. Now, we know that the energy of a K shell electron is a minimum. So, in order to make the energy of the system as a whole minimum, what will happen? There may be a transition of electron from the L shell to the K shell, or there is also a possibility that an M shell electron will come and occupy the vacancy in the K shell. Now, when this kind of behavior happens, then what will happen? This electron from the M shell, which has got a much higher energy than the electron of a K shell, if it wants to come from the L shell to occupy the vacancy in K shell, it has to give out its extra energy. So, that extra energy, when it gives out, it comes out in the form of an X-ray photon, and we call it the K beta radiation. On the other hand, when an L shell electron comes and occupies the vacancy in the K shell, then the extra energy which it has to shed, because L shell electron has a higher energy than K shell electron. So, it has to give up that extra energy in order to come to this position. So, that extra energy comes out as a characteristic radiation, which is known as the K alpha radiation. So, what will happen? So, the energy of K beta, radiation, as you can see over here, is much higher than the energy of K alpha radiation, because in this case the amount of energy the M shell electron has to give away is much larger, because the energy difference here is much larger than over in this region. So, as a result, the wavelength of the K beta radiation is much less than the wavelength of the K alpha radiation. So, this is important. Energy of K beta X-ray photon is higher than the energy of the K alpha X-ray photon, and as a result the wavelength of the K beta X-ray photon is less than that of the K alpha X-ray photon, which we really found out, as we have already seen that, the you see the wavelength of K beta is less than that of the wavelength of K alpha. But what about the intensity of K alpha and K beta? We find that K alpha has a much higher intensity here, as you can see, than the K beta. Why this is so? Well, this is due to probability. You see, when there is a vacancy in the K shell electron, then who will have the maximum chance of occupying the vacancy? Naturally, the electrons which are in the nearby shell. So, the L shell electrons will have a much higher probability to come and occupy the K shell vacancy. As a result, the K alpha radiation will be much more intense, because of probability of such a reaction taking place is much higher than the probability of this reaction to occur. So, you see that although the wavelength of the K beta radiation is much shorter than that of the K alpha radiation, the intensity of the K alpha is much higher than that of K beta. So, now we know what is the origin of the white radiation and the continuous and the characteristic radiation. Now, let us talk about the interaction between the an X-ray beam and a piece of matter. You see, ultimately we are going to use X-rays to unravel the mystery that lies inside a crystal. So, we must know how an X-ray beam interacts with a piece of matter. Say for example, if you have an X-ray beam and if this is a piece of matter, then we will see that first of all it produces heat. Lot of heat will be generated, and along with that you will produce a strong transmitted beam. So, a major part of the incident beam will pass through the matter. So, it will give you a transmitted beam, lot of heat will be generated, and a few electrons will be produced, quite a bit of scattered X-rays will be produced, and fluorescent X-rays will be produced. You see, just as a beam of electrons, when it strikes a target, it produces X-rays. In a similar manner, if we have a beam of X-rays, X-ray photons striking a metal piece, then also X-rays will be produced, and those X-rays are known as fluorescent X-rays. Now, fluorescent X-rays have quite a bit of application in chemical analysis of material, as we will see later on. So, we can produce X-rays by bombarding a target material with high energy electrons. X-rays can also be produced by bombarding a target with X-rays, and the X-ray that is produced thereby is known as fluorescent X-rays or secondary X-rays. So, this is known as fluorescent X-rays or secondary X-rays. So, you see that by interaction with matter, you can produce a transmitted beam, heat, fluorescent X-rays, and then there will be scattered radiation, as we have already shown here, the scattering process. And the scattered radiation can be of two types. One is a coherent and the incoherent type, and here the radiation that is scattered is having the same wavelength as the incident wavelength, and in the other case it has a slightly larger wavelength. Now, this particular type of scattering we will use for what is known as X-ray diffraction, and this is a very important phenomenon using which we can find out the structure of crystals easily. So, using the coherent radiation, we can find out, we can have what is known as X-ray diffraction, and that is very useful. Now, different kinds of electrons are also produced. For example, there will be photoelectrons. What are photoelectrons? When X-rays strike against a material, it will produce secondary X-rays. So, whenever it knocks out an electron from the target material, that is what is known as a photoelectron. Similarly, there will be another kind of electrons called the Compton recoil electrons. These are produced by the tightly bound electrons in matter, and the OJ electrons which are produced by the loosely bound electrons in the atoms of the target material. So, this is in totality the different kinds of effects that are produced when X-rays interact with matter. Now, I am going to tell you about how matter absorbs X-rays. As we are all aware, when you pass X-ray through a material, part of it gets absorbed and only a part gets transmitted. Say for example, say this is a material, absorbing material of thickness x. So, this is an absorbing material of thickness x. We have got an incident X-ray beam which has got an intensity I0, and we have got a transmitted beam through this matter, and say the intensity of the transmitted beam is Ix. Naturally, Ix is less than I0. Now, the fractional change in intensity when X-rays pass through this matter can be written as minus di by I stands for intensity, and it is proportional to the thickness of material it penetrates. So, if we take a very small thickness dx to the material, and we consider how much is the fractional change in intensity, then minus di by I, because it intensity decreases, that is the minus sign comes. It is proportional to dx. The proportionality constant is written as mu. So, we can write minus di by I is equal to mu by dx, where mu is known as the linear absorption coefficient of this material. Now, if we integrate the above equation within the limits, we find that Ix, the transmitted beam, is equal to I0, the incident beam, into e to the power minus mu x. So, the transmitted beam and the incident beam are related by this type of an equation. Now, instead of writing e to the power mu x, we can also write it as e to the power rho into rho x. Why we do that? Rho is the density of the material, and mu by rho is known as the mass absorption coefficient of the material, whereas mu is known as the linear absorption coefficient of a material. So, you see that the constant of proportionality mu is known as the linear absorption coefficient of the material, whereas mu by rho is the mass absorption coefficient of the material. Now, mu by rho is a constant for any material regardless of in what form it may exist, a solid, a gas or a liquid. Sometimes we have a composite material through which X-ray passes through. So, for a composite material, how much will be the mu by rho? Mu by rho, say we have a composite made up of two substances 1 and 2, and suppose the mu by rho of the substance 1 is mu by rho 1, mu by rho of substance 2 is mu by rho 2, and say weight fractions of 1 is W1, weight fraction of substance 2 is W2. So, in the composite material, the total mu by rho of the composite material will be W1 mu by rho 1 plus W2 mu by rho 2. Now, if there are more than 2 components, 3, 4, 5, you can easily find out what is the mu by rho of the entire composite material. When we have an interaction of X-rays with matter, now we have realized what are the things that are possible. Some of the X-rays will be simply scattered away in all possible directions, and in addition to that, some of the energy will also be lost when a characteristic radiation is produced, when an electron will be knocked out of the K shell. So, these are the two ways by which energy will be lost, and so far as we are concerned, we can say that the material absorbs some amount of energy while giving away some. So, the scattering and process and energy release due to the formation of characteristic radiation are the two ways by which absorption takes place in the material.